Hi, my name is Zachary Onuh, and this is my presentation for Lab 5, Challenge Your Hacking Skills. In this video, I will walk you through how I planned, organized, and performed a penetration test against my meta-uploadable to virtual machine using my Kali Linux VM. I will show you my scan results, explain how I assessed risk based on those findings, and then demonstrate the hardening changes are actually implemented on the target system. Here's a quick roadmap on what I will cover today. Part A explains how I planned and organized this penetration test. Why testing like this matters to to an organization, and how I had handled it if something went wrong along the way. Part B walks us through my actual scans using Nmap, NIPCO, and EWASAP, and NUSOS. In Part C, covers my risk assessment, my countermeasures I proposed based on those results. Then finally, Part D and Part E show the real changes I made to Metauploadable and what I learned from doing it. Before touching any tools, I started by defining the scope of this test, which was my Metauploadable 2 VM. I set clear boundaries so I wouldn't accidentally test anything outside that target. I established rules of engagement to keep the test safe and controlled the entire time. My overall approach followed the structured methodology described by ScanFund through 2008, which emphasizes planning before any active scanning begins. I also mapped out the network first, so I understood what I was working with, and I documented every step as I went, so I have a clear record to reference later. Once the plan was in place, I organized the work into clear phases with a rough timeline covering reconnaissance, scanning, and the reporting. I used my Kali Linux VM to run each of the tools against the metauploadable target in a logical sequence. So each step built on what I learned from the one before it. This kind of phase approach helped me stay organized and make sure I wasn't skipping steps. I also tried to keep my process aligned with the control guidelines from FOSS 2020, particularly around documenting and managing changes as I tested. So, why does this matter to an organization? Penetration test exposes real, exploitable weaknesses before an actual attacker finds them, which gives the security team concrete evidence instead of guesswork. That evidence helps leadership prioritize where to spend limited security budget and justify investment in new controls. This kind of testing also supports the broader risk management functions described in NIST Cybersecurity Framework 2.0. NIST 2024, and doing it regularly strengthens an organization's security posture over time, while also helping meet compliance requirements across different industry frameworks. Things don't always go according to plan. So it's worth talking about what happens when a procedure fails or a step gets skipped. My approach is to stop testing immediately the moment things goes outside scope or a failure occurs. Rather than pushing forward from there, I document exactly what happened and why. I make sure to notify stakeholders before resuming anything. Any lessons from that failure get are folded back into my procedures for next time, which lines up with the disciplined iterative approach Stanford 2008 recommended for security testing. So the next part, which is start with part B, here uh here is where I get into the actual scanning, starting with mmap. This can discover the live host and open ports on my metaplotable machine. And honestly, it revealed quite a few risky services running right outside of the box. You can see in this screenshot the detailed output from my command line session. Notably ports for Telnet and FTP where both open, which legacy services known for weak or known encryption. These early findings were really important because they directly shape the deeper vulnerability work I did later. And this kind of discoveries scanning is exactly the first step in a Stanford 2008 described in a testing methodology. Next, in part B is where I ran the NIPCO against the web server to check for common, well-known issues. These two, flag outdated software versions and some risky server, configurations. In this, screenshot, you can see the warnings it generated during the scan, including the missing security headers and a couple of exposed, directly parts that shouldn't have been publicly accessible. These findings, push me to go back and manually review the website more closely. Web, focus, scanning like this, ties directly into the risk goals outlined in the new cybersecurity framework. For this scan, I use the hours SAP, to test the web application itself rather than just the server. It found injection risk along with some weak session headings, with some weak session handlings, both of which are serious concerns for a web application. You can see the alert list is generated in this screenshot. Zap also automatically mapped out the structure of the application through its spiding feature, which helped me understand what I was actually dealing with. These findings connect directly to the access control weaknesses I will talk about in part C, and they reinforce several of the control need described in first 2020. Finally, I ran the new source scan to get a deeper, more comprehensive view of the system's vulnerabilities. Users produce a ranked list of weaknesses along with severity ratings, which you can see reflected in this screenshot. The most critical findings were outdated services and honestly some weak default credentials that really shouldn't have been uh, changed. This scan became the anchor point for my former risk in assessment, since its findings mapped clearly onto several of the control family described in FOSS 2020. Now that I had results from all four scans, I compared those findings, that is in part C. I compared those findings against current cybersecurity trends to figure out where the real gaps were. The biggest gaps showed up in patch management, authentication practices, and access control overall. I ranked each risk based on how likely it was to be exploited and how much impact it would have if it were. My gap analysis leaned heavily on the control descriptions in FOSS 20, while the broader risk categories were shaped by the framework in its 2024. This process is really what set the priorities for everything I did next. Based on that gap analysis, I proposed a set of specific countermeasures. First, patching the outdated services that scanning had flagged. Second, putting stronger password policies in place for every account on the system. I also recommended disabling services that weren't being used, since that immediately shrink the attack surface, and enabling logging, so any future incident response would actually have data to work with. Each of these countermeasures tries back to a specific finding and follows a control family described in FOSS 2020. Going into implementation, I expected fewer open ports once these changes were applied. I expected stronger passwords to meaningfully cut down the risk of brute force attacks. My mitigation strategy was built around getting quick wins first. Changes that were fast to make but still had a real lasting impact. I learned on the list privilege principle from FOSS 2020 to guide which access changes to prioritize. Overall, I expected reduced exposure across several of the most critical services identified during scanning. Having a system really comes down to removing access and services that where it's necessary, since that's what shrink the attack surface and lowers the odds of a successful exploit. My overall strategy aligned with the core functions laid out in the cybersecurity framework. Beyond this, closing individual vulnerabilities, this kind of handling also improve an organization overall security maturity, builds resilience against stress down the road. Throughout this process, I kept coming back to the control catalog in FOSS 2020 to guide specific handling decisions. This is where I actually made changes to the system. I logged in locally to Metaportable using the default password, DMS, friendly credentials. And from there, I implemented three specific changes. First, I disabled one service that was clearly unnecessary and risky. Second, I changed a weak default password on one of the accounts. And third, I removed an outdated vulnerable application entirely from the system. You can see screenshots here documenting each of these changes as I made them. I picked these three changes specifically based on cost, how quickly I could implement them, and how critical the underlying vulnerability was. Disabling the unnecessary service cost almost nothing and delivered results fast. Changing the weak password addressed a critical, easily exploited issue with very little effort. And removing the outdated application fixed something that was flagged as highly critical during scanning. This kind of prioritization follows the risk-based guidelines in FOSS 2020, balancing effort against the actual security benefit gain. Let's talk about what these changes actually fix. Disabling that unnecessary service removed an encrypted remote access path that could have been exploited easily. The password change directly reduced the risk tied to weak default credentials and removed the outdated application, eliminated a known exploitable piece of vulnerable code. All three of these fixes trace directly back to findings from my user scan area and the map to several control families described in FOSS 2020. Altogether, my exposure dropped noticeably across these three specific areas. Comparing my expectations to what I actually observed, the results mostly lined up. Open ports decreased just about exactly as I had predicted going in. Password strength improved overall, though I will admit a couple of accounts didn't get updated in this round. These outcomes reflect the kind of measurable improvement described in this framework. The small gaps that did show up were mostly due to limited time for this assignment. But on the whole, my actual results closely match what I expected. Stepping back, the biggest lesson from this whole project is that hardening a system takes a replanning and patience, and it's not something you can rush. Even a few small changes produce a noticeable reduction in overall risk, which was highly a bit surprising. Keeping good documentation turned out to be essential for tracking exactly what I changed, why. So this approach reflects the continuous improvement mindset in 2024. And going forward, I had one future test to cover more systems and go a bit broader in scope. So the last slide shows the references I used in preparing this project. Thank you for listening.